Hello, I am Dr.Sudha from Government Science College, Autonomous, Bengaluru. In this session, let us recapitulate some concepts in differential equations. So to begin with, we are going to recapitulate some of the concepts on linear differential equations of first order as well as Bernoulli differential equation. Linear differential equations. Let us see what is the definition of linear differential equation. A differential equation is said to be linear if the dependent variable and its differential coefficients occur only in the first degree and not multiplied together. So that is, it is an equation of the form a naught of x into y plus a1 of x into dy by dx plus a2 of x into d square y by dx square, etc. an minus 1 of x into d power n minus 1 of y by dx to the power of n minus 1 plus an of x into d power n y by dx to the power of n equal to f of x. Here one can observe that y and its derivatives, that is dy by dx, d square y by dx square, etc. are not multiplied together in this expression. Such an expression is said to be linear differential equation, where a naught of x, a1 of x, an of x, as well as the right hand side function f of x are arbitrary differentiable functions, and dy by dx, d square y by dx square, etc. d power n of y by dx power n are derivatives of the dependent variable y with respect to the independent variable x. The standard form of a first order linear differential equation is given by dy by dx plus p into y is equal to q, where both p and q are functions of x. Here, this equation is said to be first order linear differential equation because it contains only the first order derivative dy by dx, and it is said to be linear because the degree of this derivative is 1. A first order linear differential equation is also known as Leibniz linear equation. Dx by dy plus p dash x equal to q dash, where both p dash and q dash are functions of y, is also a first order linear differential equation. Leibniz linear equation is named after German mathematician and philosopher Gottfried Wilhelm Leibniz. To solve a linear differential equation of the form dy by dx plus py equal to q, one need to find the integrating factor, which is denoted by if in short, is given by e to the power of integral p dx, where p is the coefficient of y in the given differential equation in its standard form. And the solution is given by y into integrating factor equal to integral q, the function on the right hand side, into integrating factor plus c, a constant of integration. Let us see one example. Solve dy by dx minus 1 by x plus 1 into y equal to x plus 1 into e to the power of 3x. So this is the given differential equation. It is in its standard form. Otherwise, one need to bring it to the standard form. This is in the form of Leibniz linear equation dy by dx plus py equal to q. Here p is equal to minus 1 over x plus 1. You need to compare the given equation as well as the standard Leibniz linear equation. And we can see that p is minus 1 over x plus 1 and q is x plus 1 into e to the power of 3x. Therefore, the integrating factor is given by e to the power of integral p dx. So that will be equal to e to the power of integral minus 1 by x plus 1 dx. Now let us consider the integral in the power, that is integral minus 1 over x plus 1 dx. This is similar to integral dx by x and it is nothing but log x. But here we have minus. So minus log of the denominator function, that is x plus 1 equal to log of x plus 1 to the power of minus 1. Now let us substitute this value in the integrating factor. So we obtain integrating factor is equal to e to the power of integral p dx, and integral p dx on solving was obtained as log of x plus 1 to the power of minus 1. And we all know that e to the power of log x is x. Therefore, instead of x here you have x plus 1 to the power of minus 1. Therefore, we get x plus 1 to the power of minus 1. And it can be written as 1 over x plus 1. So integrating factor is 1 over x plus 1. So we can write the solution as y into integrating factor is equal to integral q into integrating factor plus c, the constant of integration. Substitute for integrating factor. So we get y into 1 over x plus 1 equal to integral x plus 1 into e to the power of 3x into 1 over x plus 1 dx plus c. Within the integrand, now we can cancel out x plus 1 and we get y into 1 over x plus 1 equal to integral e to the power of 3x dx plus c. But integral e to the power of 3x gives us e to the power of 3x divided by 3 plus c. Now let us cross multiply this x plus 1 to the right hand side and we get y is equal to e to the power of 3x by 3 plus c into x plus 1. And this is the required solution to the given differential equation. Now let us move on to Bernoullis differential equation. Let us begin with the definition. An equation of the form dy by dx plus py is equal to q into y to the power of n. So the difference between the Leibniz linear equation and Bernoullis differential equation is y to the power of n on the right hand side. So here both p and q are functions of x. And this equation is reducible to Leibniz linear equation and it is known as Bernoullis equation. Bernoullis equation is named after the Swiss mathematician Jacob Bernoulli. Let us see the steps to solve Bernoullis equation. Dy by dx plus py is equal to q into y to the power of n. Let us call this as expression 1. The first step is to divide both sides by y to the power of n because we need to bring it to the Leibniz linear equation form. So we need to get rid of this y to the power of n on the right hand side. So let us divide both sides by y to the power of n. So we get y to the power of minus n into dy by dx plus p into y to the power of 1 minus n equal to q. and let us call this as expression 2. In the second step, we put this y to the power of 1 minus n as a new variable z. So we are changing the variable y to z. So we need to change dy by dx to dz by dx. For that, we differentiate y to the power of 1 minus n equal to z with respect to x. And we obtain 1 minus n into y to the power of minus n into dy by dx is equal to dz by dx. But here in the first term, we have y to the power of minus n into dy by dx. So to obtain y to the power of minus n into dy by dx, we shift this 1 minus n to the denominator of the right hand side, and we get y to the power of minus n into dy by dx equal to 1 over 1 minus n into dz by dx. So this expression 2 now takes the form 1 over 1 minus n into dz by dx plus p into z equal to q on substituting for y to the power of 1 minus n as well as y to the power of minus n into dy by dx in terms of z. Now to bring this to the standard form, we need to multiply throughout by 1 minus n and we get dz by dx plus 1 minus n into pz equal to 1 minus n into q. Let us call this expression 3. This is linear in Z now. So it is brought to Leibniz linear equation and we can solve using the method of solving linear differential equations. Now let us see one example. Solve x into dy by dx plus y equal to x cube into y power 6. So first let us bring this to the standard form by dividing throughout by x into y to the power of 6. Why x into y to the power of 6? Here the coefficient of dy by dx is x. We need to get rid of this x here, so we divide by x. And here on the right hand side we have y to the power of 6. We need to get rid of this y function, so we divide by y to the power of 6. So throughout we are going to divide by x into y to the power of 6, and we obtain y to the power of minus 6 into dy by dx plus y to the power of minus 5 into 1 over x equal to x square. Let us call this equation 1. Now let us use the steps of solving Bernoullis equation. So we put y to the power of minus 5 equal to z. So we need to substitute for dy by dx in terms of dz by dx. So let us differentiate y to the power of minus 5 equal to z with respect to x. And we get minus 5 into y to the power of minus 6 into dy by dx is equal to dz by dx. But we need y to the power of minus 6 into dy by dx. So we need to get rid of this minus 5. So we divide throughout by minus 5 and we get y to the power of minus 6 into dy by dx is equal to minus 1 by 5 into dz by dx. So let us substitute these values in expression 1. So we get minus 1 by 5 into dz by dx plus 1 by x into z equal to x square. So let us bring it to the standard form. So we need to eliminate this minus 1 by 5. So let us multiply throughout by minus 5. So we get dz by dx minus 5 by x into z equal to minus 5 into x square. Now this expression is linear in Z. Since it is linear in Z, let us use the method of solving the linear differential equation by finding the integrating factor. So integrating factor is equal to e to the power of integral minus phi by x dx. So when we integrate minus phi by x dx, that gives us minus phi log x, and minus phi log x can be written as log of log of x to the power of minus phi. So e to the power of log of x to the power of minus phi gives us x to the power of minus phi. That is nothing but 1 by x to the power of phi. Therefore, the solution is given by z into integrating factor is equal to integral of integrating factor into minus 5x squared, that is the right hand side function, plus c, the constant of integration. Let us substitute for the integrating factor x to the power of minus phi. So here within the integrand, now we have x to the power of minus 5 into x squared. So we get x to the power of minus 3. Now we need to integrate x to the power of minus 3. So we get x to the power of minus 2 divided by minus 2. So minus and minus gets cancelled in this first term on the right hand side. Next, let us multiply throughout by 2 so that we can get rid of this 2 in the denominator. So we get 2z x to the power of minus 5 equal to 5 into x to the power of minus 2 plus 2c. Let us bring this x to the power of minus 5 to the right hand side. So we get 2z equal to 5x to the power of 5 into x to the power of minus 2 gives us x cube plus 2c x to the power of 5. Now we need to substitute for z. Z was nothing but y to the power of minus 5. So on substituting z is equal to y to the power of minus 5, we get 2 into y to the power of minus 5 equal to 5x cubed plus 2c x to the power of 5. Now let us bring this y to the power of minus 5 also to the right hand side. So we get 2 is equal to 5x cubed y power 5 plus 2c x power 5 y power 5. And this is the required solution to the given differential equation, which was a Bernoullis equation. Thank you.